Association of Macroeconomic Modelers has several objectives. It is focused on sharing ideas about the macroeconomics of Nigeria. It's interested in joint development of models, collaborations, both between governments, businesses, and the academics, and also to train macroeconomic modelers, analysts, and others who are interested in this research ecosystem. Of course, the goal is to create work groups, think tanks on national issues. We want to be able to provide Nigerian solutions to Nigeria's macroeconomic challenges. So I want to welcome all attendees on behalf of our President, Professor Philip Alege, to today's webinar. Our speaker today is very familiar to us. He's one of our very outstanding members, and he's no other person than Professor Olubusoye. But before we read his citation, I want to also welcome, provide us with some information about our forthcoming training. This training program is going to occur quarterly in 2025, and it's an opportunity for those who are interested, enthusiasts, early researchers, and those who want to upgrade their skill. Yes, upgrade their competency in macroeconomic modeling. This training is for you. Yes, and you can see the flyer displayed on the screen. Take time to register. For those who are members already of our esteemed group, you would have a significant discount. There's also a good package for students. Yes, students, yes, we have a very good package, and it pays to register on time. Yes, so if you haven't registered, do well to register. Yes, so I want to confirm, Prof, are you online? Yes, Prof is online. So let me quickly take the citation of our speaker so that he can have ample time to drive home the message of today's seminar. That said, Professor Olusoye Elisha Olubusoye is a distinguished professor of the University of Ibadan. He's an expert in econometric modeling, big data analytics, risk analysis, and statistical computing, with a strong focus on applying advanced statistical techniques to economic and energy-related research. He was formerly the head of the Department of Minerals, Petroleum, Energy Economics, and Law, DIMPEL, at the University of Ibadan, an interdisciplinary department focused on energy policy, natural resource management, and economic development. As the director of the Center for Petroleum, Energy Economics and Law at CPIL, he played a key role in driving research and capacity building initiatives in the energy policy, energy transition, and climate change economics. Although his academic background is in statistics, he has collaborated extensively with energy experts, contributing to energy sector projects using advanced data science techniques, economic modeling, and predictive analytics. Professor Olubusoye is a senior research fellow at the Center for Econometric and Applied Research, CIE, where he has been involved in multiple research projects related to economic modeling, macroeconomic policy analysis, and statistical forecasting. His work has been instrumental in shaping energy market research and supporting policy recommendations for sustainable energy development in Nigeria and Africa. His professional affiliations and recognitions. He is a member of several prestigious professional and academic associations, including the Nigerian Association of Macroeconomic Modelers. Yes. His research training and consultancy. He has also collaborated with leading international organizations, including the IMF, the World Bank, the African Development Bank, and USAID, and on projects ranging from economic modeling to energy policy and financial risk assessment. He has led and facilitated numerous training programs on big data analytics, machine learning, and policy modeling, particularly for government agencies, financial institutions, and the central bank, CBN. His research contributions span across energy pricing and forecasting, macroeconomic and financial market modeling, machine learning applications in economic and policy research. He has published extensively in high-impact journals with contributions to international research on energy economics, inflation modeling, and data-driven decision-making. His work continues to influence academic research, policy frameworks, and industry practices. As the coordinator of the University of Ibadan Laboratory for Interdisciplinary Statistical Analysis, that is UI-LISA, Prof has been instrumental in advancing statistical capacity in Nigeria and Africa. He has mentored numerous postgraduate students and young researchers, fostering the next generation of experts in statistics, economics, and data science. With a career dedicated to research excellence and evidence-based policymaking, Prof remains a driving force in applying data science and statistics to solve critical economic and energy challenges. Ladies and gentlemen, please join me to welcome Professor O.E. Olubusoye. Prof, you have the floor.
Thank you very much, Dr. Wobi. Let me share my screen now. I hope you are able to see my screen.
Yes, Prof, we can.
Yes, sir, we can.
So, good afternoon, distinguished participants. Let me start by appreciating the president of NAMM, Professor Alege, and the executive members for giving me this platform, and also for initiating this webinar series as part of the association's agenda to promote evidence-based decision-making and build the capacity of early career modelers in Nigeria. Our time is so short, so we'll go straight to the package for today. The focus will be on statistical modeling essentials, foundations for accurate insights. And I will be looking at the foundations and basic concepts that modelers, particularly early career modelers, need to get familiar with. But why is this so important? Why this topic in the first instance? Today's world is driven by two things. One is driven by technology, and is also driven by data. Data is coming in large volume and high speed. To make sense of this data, to uncover patterns, to make predictions, to support decisions, statistical modeling cannot be overemphasized. So the focus, the goal of this webinar actually is to share the foundation principles of statistical modeling. I emphasize statistical modeling. There are other types of modeling, but the focus here is statistical modeling. And then our goal is to see how to build models, not only for businesses, for industry, but even for the economy. Models that can generate accurate insights. So the statistical modeling in this age is very, very crucial. I mean, the ability to formulate and use statistical models are very crucial for this, for businesses, for researchers, for policymakers, to support decision making. So statistical model itself helps to move from data to insights. You have data in raw form, which sometimes could be messy, and statistical model can turn this to actionable knowledge. So modeling, whether statistical or econometric, or as the case may be, they have real-world applications in the economy, in health, in fraud, in climate. You can see all spheres of human endeavor can have the benefit, can benefit from statistical modeling. And just like somebody said, without models, we are just guessing. And guessing has never produced the best option for anyone. So this is the broad overview of the key topics I intend to cover in this discussion. I will look at the foundations of statistical modeling, the basic things that make up the statistical model, the components and all of that. And then we'll have a quick glimpse of the types of statistical models that we can have. We will run through the process, the statistical modeling process. What are the various stages to guide those who are in love with modeling? We will look at essential concepts like bias, like variance, like overfitting, underfitting, optimal models, and things like that. And then we will look at common pitfalls and also emphasize best practices as far as statistical modeling is concerned. So if we say statistical modeling, essentially we are talking about a process which involves using mathematical frameworks to represent relationships, physical relationships. So that involves looking at relationship between variables and getting data and fitting models and using the model to make decisions or even build scenarios. So statistical models enables one to identify patterns in data, make informed predictions, test hypotheses, and draw conclusions. It also helps to support decision makings, looking at possible options and the risks associated with those options. A key component of statistical model Here we have 4 major components of a statistical model. The raw input, which are the observations, the data points. Then the features that define the model, which are variables that are measured or directly observed. And then the mathematical relationships represented by equations, which shows the dependencies, how the variables are related. And the fourth component are the assumptions that underlie the conditions that must hold. These key components are very, very important, and without them, you cannot even formulate a useful model. But in terms of the variables, variables are here categorized into 4. If you are modeling, it's always the starting point is to know the outcome you want to predict or you want to explain. That is the dependent variable. The factors influencing that outcome variable is independent variable or the predictors. So they influence the outcome variables. But dependent and independent variables could be categorical or continuous. A variable is categorical if the variable represents groups like gender, product type, and etc. It's continuous if it's measured, and it can take value within a range of values, like income, like temperature, and all of that. So it's very important to know how your variables are measured, how your dependent variable is measured, and how your independent variables are also measured. Another sort of key concept are parameters and statistics. Our models, we have parameters which represent the characteristics of the population that you really that is unknown and that you want to measure. The statistics is the estimate that you derive, using your data, because you don't have the data you have is not the universe. So your data represents a subset of possible data of the collection of possible observations that you can gather from the population. So your model will have parameters, but your statistics enables you to estimate using your data the values of the unknown quantities in the population. It's always very important to associate distributions, standard distributions to our variables. That is important because we need to have a good understanding of the data generation process. So the distributions gives a sort of standard behavior of the variables over time. So common distributions that one can think of listed here, the normal, and you use this when your variables are measured on the continuous scale, like heights and stock prices. You can assume that your data generation process comes from a binomial distribution if the variable is binary. In other words, it's taking only two categories: success, failure, pass, fail, and so on. If the measured variable is discrete, is count, so you can use horizontal distribution to represent the data generation process, like in the case of calls per hour in the call center. So distributions are very crucial in statistical modeling to represent the data generation process. In statistical modeling, data can come in different forms. We now have structured and unstructured data. Structured data are well organized. They are in rows and columns. They are in databases. They are in spreadsheets. Unstructured one can be text, images, and videos, social media data. These days, you have more of unstructured data. People also talk about semi-structure. Data can also have time dimension, the temporal, and then the space. So you have the cross-sectional data. So when you have your data gathered over time, then you have time series. When you observe your data at a point in time, but across individuals, then you have cross-sectional. Of course, combining the two, you could also have panel, or longitudinal, as the case may be. You could also have data from experiment as against data from direct observation. In most experimental sciences, you could control the conditions and then observe how the outcome variable changes. That's experimental if you are controlling the conditions. But for observational data, you are not able to manipulate the data. And so these are the different data structure. Why we are listing them is any modeler must be able to know the category of data he or she is working with. So why do we need statistical models? We want to describe, we want to infer, you want to predict, you want to also establish causal relationships. So these are four major reasons statistical models could be helpful. And the models, the key model categories are descriptive, inferential, predictive, causal, and now we have the machine learning models. Each of them will take and then look at when we use them and what they can give. The descriptive model is basically aimed at helping us to understand the data, draw insight from the data, to summarize it and to organize it, to be able to identify common or salient features in the data. It doesn't make predictions as such, and it doesn't draw inference about relationships, but basically to describe the features of the data. So you use tools like measures of location, measures of spread, measures of partition, and so on. So you simply describe the location, you describe the spread, you describe the shape. That is what data visualization helps you to do. So, but the second type of model, inferential model, beyond describing, you can also make, from your sample, you can generalize about the larger population. And the beauty of it is that you are able to quantify the uncertainty using probability to measure the confidence, the uncertainty around whatever estimate or whatever conclusion that you are trying to draw. So you can use techniques like hypothesis testing, confidence interval, MOVA, and all of that. We are quite familiar with that. The third type of models are meant for forecasting future outcomes. And here you rely heavily on historical data to be able to predict future outcomes, patterns. They are commonly used in businesses. So models like linear, can help linear regression, logistic regression, polynomial regression. They can help you to make prediction, but it depends on how the outcome variable is measured. If the outcome variable is measured on a continuous scale, then you can use linear regression. The outcome variable is measured on binary scale, then you use logistic. For polynomial regression, when you handle non-linear relationships. There are other models not listed here, which are quite advanced. But another group of models which will help to establish cause and effect relationships are called the causal models. This type of models, they identify how variables impact on one another, and then controlling for potential confounders. So they can help policymakers, social scientists, and economists trying to come up with policy or interventions. The common causal modeling techniques which fall in this category are the structural equation modeling, difference in difference, and then the instrumental variables. The topical one now, that's the last group of statistical models, are the machine learning algorithms, techniques. They have also, they are beginning to play a huge role, and they are being combined also with statistical models. When do we integrate the techniques, the machine learning techniques with the statistical model? There are situations when statistical models they may not be sufficient to handle the complexity of the phenomena that one is trying to model. So in that instance, machine learning will really help. Instances where you have large data sets, so you have large observations running into thousands and millions and so on, or when you have high dimensional features, you have variables also going into several millions, then you might want to integrate machine learning technique. So you could employ supervised learning, which could be regression or classification techniques, depending on whether the outcome variable is continuous or whether the outcome variable is categorical. You could employ unsupervised learning, and that involves clustering. So clustering will help you to group individuals. Principal component will help you to group variables. You could also employ deep learning, which is an advanced neural network used for pattern recognition. Now, I'm moving fast because of the other things that we still have to talk about. Here, we want to look at the process involved in statistical modeling. And I have I've itemized about six steps here. So we'll quickly take them one at a time. The first is to define the problem. And this will require asking concrete questions. Questions like, what is the objective? Are you predicting? Are you drawing inference? Are you using the model to explain the phenomenon? So any of these three could be your key interest. What are the key variables? And in that, you need to know which variable is your outcome, which variable are your predictors or features. Who are the stakeholders? What are the constraints in terms of data availability, in terms of scope, in terms of computing resources? So to define the problem, you need to ask key questions. The second step is data collection and preparation. Once the problem is defined, then the variables are decided, and other key key questions are answered. Then you have to gather the data, and you could do that through surveys or looking for databases online, anywhere. You could also go for web scraping. You could also conduct experiments and observe your collect your data from the experiment. So, but data preparation will follow once you have gathered the data. And it's always important that this aspect may take 80% of your time, data preparation, ensuring that the data is cleaned, and by dealing with outliers, missing values, ensuring that variables are standardized, putting them in standard formats, and then breaking or splitting the data into training and testing sets. These are data preparation steps. After that, once you have your data clean, then you need to conduct exploratory data analysis. Exploratory data analysis is very important because it gives you a sort of indicators or sort of ideas about the patterns and the distributions, the way the variables are related, the way the variables are connected. So you have that preliminary information from your exploratory data analysis. From there, you can identify correlations, you can identify anomalies, you can identify missing values. From your EDA, you can, also begin to prune down variables or features. The predictors, you can prune them down because you begin to see variables that are not really relating with your outcome variables. This aspect is what we call feature selection and engineering. So EDA generally involves you conducting summary statistics, using visualizations, and also employ correlation analysis. The fourth step is to now begin your model selection and model building proper. This involves forward, backward kind of procedure. So you have to now begin to search for the right model. You are searching for the right model in a very dense model space. So in that space, there are several models, and it's not easy to just come up with one model. You have to convince, and you have to do a lot to even settle for one model. So to do that, to choose the right model, you employ descriptive, the other techniques that we have earlier listed: descriptive, inferential, predictive, causal. All of these will have to go into the process of choosing the right model. It's always funny when people, modelers, come up at the end of the day with one model, without telling us other competing models. It's also good that we know the other competing models and how you eventually, settle for this final model. To do that, you have to employ all this arsenal to choose the right model. So the model building process will start with the formulation of the mathematical relationships, the training of the model using historical data, and then the continuous fine-tuning of the parameters to be able to achieve optimal, to be able to get the optimal model. Once the optimal model is obtained, you need to evaluate. And sometimes also evaluation will cover other competing models. So the purpose of evaluation is to ensure model reliability and accuracy. At this stage, you want to detect if your model is too complex, that is overfitting, or your model is too simple, that is underfitting. I will still talk more about those concepts shortly. You also want to employ a number of evaluation metrics. Sure, most of us are familiar with some of them. So if you are dealing with regression model with continuous outcome, then the evaluation metrics could be R-square, root mean square error, and a host of other ones. If it's classification, then you have to use metrics like accuracy, precision, recall, F1 score, and AUC, so on. So then for machine learning, you employ the cross-validation techniques, which requires splitting the data multiple times to test for model consistency. So cross-validation is a critical step to be able to evaluate how your model is able to perform outside the data that you use to estimate its parameters. And of course, the last step is once you have a final model, then you need to interpret the model and also communicate. But it's always good that your output is meaningful, sensible, and is something that can be implemented. So you also need to be sure that your model, the underlying assumptions, your model are met and satisfied. And then those that will consume the outcome of your, whatever comes from your model will not be technical people. Need to bring the discussion or the interpretation down to the level of non-technical stakeholders is very important. So the best practices as far as communication of the results is concerned is to use simple language, use visualization, and then always tie your communication of the statistical results to the practical application, the implication, business implication, or economic implication or social implication must be emphasized. Now, I want to quickly look at essential concepts in statistical modeling. This is the most important part of this discussion. Why are these concepts important? Because they are necessary for us to be able to ensure accuracy and ensure generalizability of our results. So we will talk about the concept of bias-variance trade-off, the concept of overfitting and underfitting, and then the concept of model validation and cross-validation. Let's start with the bias-variance trade-off, which is a major challenge in statistical modeling. When we talk of model bias, we refer to errors that introduce when your model is oversimplified. The relationship is non-linear, but you assume linearity. So you oversimplify that relationship. So that is captured in terms of model bias. And if the model is too simple, the danger is that it will fail to capture the patterns. So that's what we call underfitting. That's when we have high bias. So high bias is linked to underfitting, and is when your model is too simple to really track the inherent pattern in the data. When we talk about model variance, we are looking at how the model fluctuates from one data set to another data set. For instance, you split your data into training and test set, and your model performs very well in the training set, but is unable to perform in the test set. Then the variance is high. We will say high variance, because the model is too complex and it's only capturing the noise, not the signal. And that's when you have high variance. So a modeler should be able to understand these two concepts and strike a balance. And I will explain how that balance, which is called the bias-variance trade-off, how you strike the balance between overfitting and underfitting. If you look at this diagram, on the vertical axis, that's where you have the error. And on the horizontal axis, that's where you have the model complexity, which means when the model is simple here, and as you had maybe more variables or more observations or more functions, then you complicate the model. So model on this horizontal, you are looking at from simple to next models, and from small error to large error. Now the green one here represents the variance, and you will see the behavior of the variance. The bias is the one that is it red now? Now, the blue one is the total error, which is the total bias square and the variance. So, but let's look at when the model is simple. At this point, you notice the variance is very small. The total error is very small. But the bias square is very, very high. And as the model complexity grows, you see the bias coming down, and then the variance increasing. So when you have a very complex model, you tend to have high variance. And what high variance means is that your model is unable to perform outside the data that you use to train it. So it's not able to capture the inherent, the natural, movement in the data. But it's able to do it very well in the data you use to train it. But the total error is, you can see the shape. Initially, it decreases, the total error decreases, and then after this point, it increases. So which means as the model becomes complex, initially you gain because the error will be reducing. The total error will be reducing, which is the error arising from the bias and the variance. But it will get to a minimum point that further expansion or further formulation of the model in such a way that it becomes complex will no longer yield any gain, but rather the total error will be increasing. So the point where you should stop complicating the model is the point where the bias and the variance are the same, and that is the optimal solution. So it's always good to understand this thing. You really don't. Most modelers will prefer to bring all possible features, incorporate all possible dynamics into the model. You may gain a little, but you may also be losing once you go beyond the optimal solution. So, and as you see here, you have underfitting. This is the underfitting zone. In the underfitting zone, the bias is greater than the variance. In the overfitting zone, you see the variance is greater than the bias. So you want a situation where there is equilibrium between the bias and the variance. And so finding the right fit, which I've explained earlier, you must know that underfitting implies that your model is too simple. So, and that will give you high bias and very low variance. Overfitting will give you low variance, low bias, but high variance. So it's always good you have a model that will detect the signal and also detect the noise in a balanced style. So how do you fix overfitting? You might need to use more training data to address the overfitting, because if the training data does not contain all possible dynamics and patterns in the data, then in the test data it will not be able to perform as in the training set. There are also techniques, regularization techniques like lasso and ridge techniques, which can help you to remove variables that are not important, so that the degree of the complexity is reduced. So these are possible solutions that we want to consider. So I've talked about this. Let's move on. Then the issue is, how do you now ensure optimal? The optimal model is achieved using the model validation approach. So it ensures that the model's predictions are reliable, and then the validation helps to detect overfitting before deployment, and then it helps you to choose the best performing model. So common validation techniques include train, test, split, splitting the data into training, and the model learns from the training set, and then the testing data is used for the evaluation, and then the cross validation is repeated over multiple data subsets before you get, before you can be convinced about the performance of that of the model. So there are different splitting ratios, 80-20, 30-70, that is maybe 80 for training, 20 for testing. There is no consensus in literature of the appropriate splitting, but it's always good as part of the validation process to try different splitting ratios. So cross-validation techniques could be K-food. We have several of them, but I just mentioned these two. K-food, leave one out, cross-validation. These are, but there are other advanced techniques. We're almost done. Common pitfalls and best practices in statistical modeling. We need to be conscious of the common pitfalls. I have a few of them here, and then we will then close the discussion with best practices. We need to have this firm understanding that to improve the reliability of our models, statistical models, we need to find ways to avoid errors as much as possible. Errors can come from the data, error can come from the specifications, error can come from the estimation, error can come from even the validation, and all stages of the modeling you can have you can encounter error, but ability to avoid those errors is a way to guarantee the reliability the models. So let's look at the common pitfalls, starting with when we misinterpret correlation as causation. Misinterpreting correlation as causation is an evil that is widespread among modelers. 2, ignoring outliers and missing observations. 3, over-reliance on p-values. And lastly, violating model assumptions. But let's quickly look at the...
Prof, it's 1 o'clock, sir. We're out of time.
Oh,
yes.
Okay,
we will not be able to take questions or comments here on this platform. We'll have to switch to WhatsApp.
No, I can talk now so that questions, maybe 1 or 2 questions. Sorry, I didn't know.
We're out of time. Yes.
Oh,
so we need to also stick to time. Our Muslim brothers and sisters would need to go and pray, especially in this season of Ramadan. So we need to respect that. So I want to say the President, Professor Philip Alege, will quickly give closing remarks for us to conclude. It's been an interesting time. Professor Alege, sir.
Oh, thank you so much, Dr. Lucy, for a wonderful coordination. And I want to thank Professor Olubusoye for an erudite presentation. You can't have better than this. In fact, he has trained and retrained all of us in statistical modeling. And for any one of us to benefit from what we are doing at NAMM, this training is just crucial for all of us. It's the basic thing that we must know. And I think he has dealt with every aspect in which we all must know, and to give us a good insight of our modeling. The models are not just for nothing. When we say evidence-based, it's because we are using data to look at what is happening now, what may be happening before, and what will happen in the future. So on this note, I want to thank you all for coming, and we are waiting for you next week for our first set of trainings, and we hope and we know it will be beneficial for every one of us. Thank you all.
Thank you very much, Prof. Our president has spoken, and we come to the end of today's webinar. I believe it was worth your time. Questions and comments will be taken on our WhatsApp platform, so that those who want to join NAMM, the registration link is in the chat box. Yes. Thank you so much for coming, and good afternoon.
Good afternoon. Thank you to everybody. Welcome.
Thank you, Prof.
I can see you. Professor Olubusoye.
Dr. Lucy, good afternoon.
That's wonderful.
I didn't. Time flies. Time flies.
That was very good.
I could see that I didn't know.
I didn't. Prof.
So, that was very good. Vice President, very, very good.
Thank you, sir. Thank you, sir.
Very good presentation and outing.
No, nobody should miss this this lecture. Thank you so much, President. Yes, it will be done.
Okay.
Yeah.
Wonderful.